As indicated, this is about scientific matter, but also historical one, the large-scale dynamics of laws, facts, and proofs. It will visit the 1D Burgers equation and the 3D Euler and Navier-Stokes. And this work has been done in very close contact with Rahul Pandit and Deepanka Roy, and in very close association also with Alexei Mailev and Takeshi Matsumoto, but that would be too much. So the paper will present all these things. So this part will just talk about part of what we've done. So let me go back roughly 5 centuries. There to Leonardo and Turbulence along the famous river Arno in Florence. Leonardo made some inscriptions here on the left. You cannot read them unless you are very good at mirror reading. But if you turn it upside down, then you can begin to see here is turbulence, turbulence, turbulence. The Italian is written there, the English is there in English, where the turbulence of water is generated, where the turbulence of water maintains for long, where the turbulence of water comes to rest. What he was observing, Leonardo, was the eddies, he called them turbulences, by the way, generated along the timbers of at that time there was a single bridge, I believe, crossing the Arno River, and observing them how they decay to rest, and doing so very slowly. Don't forget at that time there were no exponentials, no logarithms, no power laws. So the only way he can describe that, even although he was observing them not from outside, but also from inside with special goggles to watch the eddies and so on, the best words he could use are those. Now, there is something paradoxical, because the place where you find these messages is the famous Codex Atlanticus, not named by Leonardo, but after him, which has more than 1,500 pages, double-sided. The person who assembled these things and then popularized it was a certain Pompeo Leoni. But the manuscript had stayed with him for maybe 70 years or so. And Pompeo Leoni assembled this just by, not exactly by luck, but things that look nice. But he made some grievous mistakes, because not knowing the evolution of the handwriting of Leonardo and knowing very little about his scientific activity, Pompeo Leoni put this thing around 1470, which is when Leonardo was not quite 30 years old. At that time, we know that Leonardo had no interest in fluid dynamics. So it took a very long time until modern scientists living in the 20th century found how to date this correctly. And that was done by Augusto Marinoni from Milan. And he dated it in 1505, roughly 25 years later, actually more. So, well, it's late, it is about 27 years old, but one doesn't know exactly. So, and then it puts this work in the burst of activity that started with Leonardi in the early 16th century. This was particularly important because Leonardo, who had left Florence for Milano, eventually he returned to Milano and got involved in understanding how the river Arno could be mastered in such a way that it could become navigable all the way to the Mediterranean. And he established that it would require tens of thousands of workers working for a very long time, something that exceeded the budget of anybody there. So this was abundant, but Leonardo spent a lot of time studying the river and diving into it and finding out how the eddies or the turbulences were acting there. And so it is very good to have this date of 1505 correct. Now, what is curious is that it took a very long time until people developed the ability to study the decay of eddies or turbulences, and that will be in the next slide. So the names are Karman, Kolmogorov, Proudman, together with Reed, and what is called weak and strong solutions. So this is one of the most important slides of my talk, so a kind of summary. So Karman, that was in 1938, and Kolmogorov just about 3 years later. They speculated that in the limit of vanishing viscosity and in the absence of forces, that's very important, the absence of forces is crucial, that the energy of three-dimensional incompressible turbulence would asymptotically decline as a power law, so that the energy E of t goes like t to the minus n. Then happened is that Karman, who had got some of his inspiration by a paper of G.I. Taylor, in the paper that he had written with Howard, he added a new section at the very end, signed just by him. That's just by Karman. And he tried to figure out which power of time, which inverse power of time would be relevant in the decline of eddies in 3 dimension. But he made a trivial algebraic mistake, which was captured 3 years later by Kolmogorov. Now, Kolmogorov, in his second paper of 1941, not the first, he also made a conceptual mistake by using an invariant discovered by a Russian, Rozyantsy, and Kolmogorov obtained this decay law, which goes T to the minus 10 over 7. It took some while until in 1954, Proudman and Reed discovered that the Lojzhansky invariant is typically infinite, thereby invalidating Kolmogorov's 1941b. Nevertheless, Kolmogorov's 1941b paper contains a most important result regarding energy dissipation, even if one ignores the Lojzhansky. So I will return to this at the end of the talk. Now, much more recently, published in 2019, the investigation of Buckmaster, Delelis, Shekelidi, Vicol, using so-called weak, that means distributional, solutions of the 3D incompressible Euler equation, show that the evolution of the energy is compatible with an almost arbitrary change in time of the total energy, subject only some mild conditions such as the boundedness of the time derivatives and so on. Then just after that, in February 2019, there was a meeting in Nice with Takashi Matsumoto and Leslie Sekelidi, and we had discussions centered around these solutions, but now considering so-called strong solutions, so that real solutions. For example, zero viscosity limit of Navier-Stokes solutions. And then the question was, can strong solution display a long time decay of the energy, which does not follow a Karman-Kolmogorov power law? Because when I discussed the solution, the so-called weak solution, with a number of colleagues, they said, oh, these are just weak solutions. Strong solution will never displace that. And I doubted that. And as you will see, now we have very strong proof that the solution, the type of solution invented by Kolmogorov and Karman are definitely not the only ones. And there are things which are not pure power laws. So how to do that? Now this problem can be addressed fully by using the Burger's equation. Now the Burger's equation is actually a very tough thing, but I don't have time now to explain you why a number of people have fought with the Burger's equation, obtained highly non-trivial results, but just don't make the mistake to think that if it's Burger's, it's trivial. Not at all. So the Burger's equation, of course, is written. Anything that is highlighted means is a more important concept. Everybody knows the Burger's equation, so that's not. And one important feature of the Burger's equation, which is discussed in detail in the book that Burgers himself produced in 1974, and which he seems to be attributing to Hopf. But when you look at the paper of Hopf, it's not clear that it is there, but Burgers was a very nice person. He didn't mind people making progress on his equation. So, and which I will just call it the Max formula. This is something, this is rather well known, but it tells you that in the limit of vanishing viscosity, the potential, so that the velocity is minus the spatial derivative of the potential at time t is a maximum over the initial coordinates, or Lagrangian coordinate a of the initial potential, phi 0 a, and then decorated by a parabolic term. Now, a very important property of this, when you look at this maximum thing, you can expand the quadratic term, and then some trivial changes of variable show you that basically you have a Legendre transform. And that is very important because it means two things. One, that you can go directly from the initial data to what's the time t without going through intermediate times. And that furthermore, because it's a Legendre transform, it can be obtained in a very small number of steps, basically something that varies like the resolution times the logarithm of the logarithm, so that one can do these things very efficiently. So the first who observed this was Jan Brognier. So let me go to the next one that is here. Yeah, so of course there is an important difference between the Burgers equation and the Navier-Stokes equation, is that the Burgers equation has no mechanism allowing to generate stochastic equation unless the initial conditions are assumed stochastic. So the thing on which we concentrated mostly is the case where the initial data in space is Brownian motion, in space, not in time, in space. There's no need to define to you what Brownian motion is, but we will also work with generalization of Brownian motion, which were discovered by Kolmogorov in a paper just 1 year before the famous turbulence paper. And these are be called later fractional Brownian motion. They are processes which are Gaussian and which are sort of variants of the Brownian motion that have a power law spectrum, but not the same power as what one assumes for stored standard Brownian motion. And you will see that the mixture of various type of solutions with different control parameters, they are called the Hurst exponent, will lead us to what is now called large-scale multifractal extension of Brownian motion. Something that seems to be unknown so far, to the best of my knowledge, since I know something about multifractals, is they were exclusively used on small scales, not on large scales. So the first thing that we need is a thorough theory of the decay, not just for Brownian initial data, but also by fractionally Brownian motion, because unfortunately the standard Brownian motion is a Markov process, but its cousins are certainly Gaussian, but they are not Markov processes. They have other properties, which are known, at least by two mathematicians, as semi-martingales and so on. We don't have to go into that zoo of mathematics, and that has still a number of questions that are open, but it's important to realize that this is touching on the frontiers of probability theory. So one of the first things that we has to realize that Brownian motion is not a spatially stationary process. It is not directly a translation invariant. However, its increments are translation invariant. So when you write that in with Brownian motion, then you get a semi-horrible equation, which I did not highlight, but is almost equivalent if there is a place, a Lagrangian coordinate, where the initial potential vanishes, you can then just subtract this thing and you obtain this highlighted thing, which tells you that if you have a scaling factor lambda and you go from A to lambda A, then this basically means that you are multiplying your process by a lambda to the h. You could put it in the right-hand side if you wish. But this is only probabilistically. It is it's called there are two names for it. One is to say that it have the same law, and other people say that things are isonomic. Isonomic means the same as having the same law. That means that probabilistic laws are the same. So these are the thing with which one has to work. I'm changing transparency. Yeah. Excuse me. Now, here, first we have to go and look at what physicists have done on the decay of burgers, in particular in the work that was started by Gorbatov and others, including the chairman of this meeting, including myself and others, in '97. What was done, power laws, but obtained by phenomenology and not rigorous mathematical approaches. The first rigorous mathematical approach for Brownian motion was done in '95, that's 25 years ago, by Avellaneda and in the United States. And that is for strict Brownian motion. And they used heavy machinery, probabilistic machinery, and were able to derive the properties of these things. However, anything which is not a Markov process, that was a bit more difficult. And so that stayed unknown for quite a long time. And that's why I will show now to you, without using heavyweight mathematics, that when the first exponent is not 1/2, so it's not standard Brownian motion, the decay of the energy at large times is a power law but with an exponent which depends non-trivially on h. Now let's see how that is done. The basic idea is to use the scaling invariance. So changing the lambda coordinate, the a coordinate into lambda. Lambda is a scaling factor. It has to be positive, and you just change a into lambda a. You change x into lambda x, and substitute in the maximum formula. Then you use the scaling inversion, and you get an equality in law only. Now, the trick here, which I think is mathematically respectable but understandable, is that now you have a combination of the initial data with a factor lambda to the h, and of the parabolic term with a factor lambda squared over t. Now, suppose that you demand that the two factors be the same. Then you can pull out a factor, and you reduce the thing to the solution at some reference time. You see, you can take a reference time t star, never mind what it is, and then you can go from t star to t. That is a certain factor. These factors combined with the lambda squared can match the lambda to the h. And that happens precisely when the scaling factor and the time, more precisely the time dimensionalized by the reference time, is this thing. And this way, you can immediately find how things decay in time, because now the law of the potential is that you take the potential at the reference time, and then you go some other time, you just have to multiply by a factor lambda squared over t minus t star, and that will be okay in law. But that's very powerful, because you will see in the next thing here, if you know how the potential varies just by taking derivatives, it's trivial to find how the velocity varies. And then, since you know the law of the velocity, you can square, and you will know the law of the squared velocity. And then you can average that probabilistically. And here you have it. You will find that the squared velocity is expressed in terms of the velocity at the reference time by this thing. This is not in law anymore. It is an equality, because we have averaged, so the probability has disappeared. And in this way, you find that the decay in time for the case of a single Hurst exponent is just a power law. However, now, what do you do? All right, so now let me explain now why these Brownian motion, including the generalized Brownian, the fractional Brownian motion, have a very, very nice property. So I will use some slightly more elaborated mathematics, but trying to not terrorize those who are not probabilist. First, this is supposed to be some Brownian motion, not necessarily the standard Brownian motion. It can be also a fractal Brownian motion. What is important is that it is not differentiable. Everybody knows that Brownian motion is continuous but not differentiable. This property is shared by fractional Brownian motion. Now, you remember that there is this max formula. This max formula tells me that one can change the initial data of the initial potential to what it should be at some later time by adding a parabolic term, x minus a squared over 2t, and taking a maximum. Now, if you expand this parabolic term, you will get three terms, x squared, a squared, and minus 2ax, of course. You can put the x term, you can put in the left-hand side. The a squared term, you can add it to the initial Brownian potential. So it becomes a slightly modified Brownian thing. And then what is ax? Ax, when you take a function and you add ax and you take the maximum, and it's just a Legendre transform. So all the ingredients are there, but you cannot escape. When you want to do the rigorous mathematics, you have to use Girshanov's result, which is published in 1960, yes, which tells us that if you take something like Brownian motion and then you add a nice term like a squared, which is nice and smooth and so on, then of course the places where the thing lives are changing trivially because you add something. But because what you add is very nice, the differentiability is not basically changing. And that what implies that when you take the Legendre transform, which geometrically amounts to constructing a convex hull of the Brownian motion or the generalized Brownian motion, then the places where the Brownian motion and its convex hull touch are separated points. Of course, you can guess that this will be true just because Brownian motion is not differentiable. Therefore, you can. It is hard to imagine that the convex hull could have entire segments of contacts between the convex hull and the Brownian motion, but one can prove such things. Now, once you have that, since the limit will be involve only the convex hull, when you transfer this to the velocity by taking a gradient, you obtain the right figures. Namely, there in Berger's jargon, you have shocks, but between the shocks, you have a straight ramp. Why is that? Just because the only thing that changes there is x minus a squared. A doesn't change. X changes Yes, but that in a quadratic way, and when you take the derivatives, you get something linear. So this is a very nice thing, and which imply something which for me was a bit amazing, the solution of the Burger's equation with Brownian initial data is completely self-similar, starting from 0 to any time. Of course, with a highly singular behavior at time 0. At time up to time 0, it is continuous but not differentiable. At any time greater than 0, it will have shocks, but nice things in between the shocks. So now I come to the solution which will have the multifractal behavior, which is obtained by putting together all kinds of Brownian motion. How is that done roughly? Well, you assume that the initial potential over a certain range of scales is stupid Brownian motion at some other range of scale is a different Brownian motion with another Hurst exponent, etc., etc. But to do this correctly, you have to work in Fourier space. And but it is actually not particularly difficult. You can split up things in Fourier space in a way which is completely rational even from the mathematical point of view. And then what will then happen is, I'm going here to this, yeah, there's something that mathematicians will like. In Fourier space, you split up things in Fourier space, spatial Fourier space, into intervals or unions of intervals, which are disjoint things and have different Hurst exponents. And you can do that systematically. And at the end, you can then obtain the law of evolution, because there is more than one Hurst exponent. It can be infinite many Hurst exponents. In this case, we have taken 3, but that's it. And you find that the maximum formula goes over, instead of having just one term, there are 3 terms, for example, corresponding to the 3 Hurst exponents which are present. But of course, the parabolic term is not changed. And one can do these singly and study them in detail. And what's important, because with Burgers, you are able to write the solution directly from the initial data. You don't have to go through intermediate steps, so that a formula such as the one that is highlighted here can be studied by hand. It is marginally more convenient to do it on the computer, but you don't really have to do it, because everything is in terms of the initial data. So you obtain complete control of what is happening. And if you want to do this numerically, then you have a slightly unusual situation. It is something that I discussed briefly with Heire in the discussion session of the other day. Namely, instead of having the situation where you have the theory on one hand and then the full numerical simulation on the other hand, you have a mixture. You can do the theory completely, but you can do some relatively trivial steps numerically, but it just saves time. It is actually a kind of computer-assisted theory. So here you see, for example, that with Brownian motion, having a certain central Hurst exponent 0.45. This is not far from 1/2, and then two other Hurst exponents differing by plus or minus 0.4. You find that the decay in time of the total energy isn't a power law anymore, but because of this multifractal thing, it has undulations. You see them more clearly by writing the local slope, but that's the local slope of the other graph. So these things are not power laws. And if you look at the spectrum, spatial spectrum, instead of being a power law, it is also something that undulates. So there is no doubt, this took us a very, very long time, in particular because we were trying to find solutions going through the complex plane, and they were non-solutions. So the multifractal approach here is crucial. And so there is no doubt now that the Burger's equation have such solutions which are not just decaying purely as power laws. Now, finally, I want to go back to the paper of 1941b. There is a little stangle concerning this paper, because the paper was considered, after the work of Proudman and Reed, wrong because it was using the Lagrangian invariant, and people completely forgot that Kolmogorov had in this paper a very, very nice law for the decay of turbulence, which does not use the Lagrangian. If you take the paper of Kolmogorov and do very slightly modernize the notation, just to make more contact with the current, you find that the time derivative of the total energy is within a positive constant, the energy to the power 3/2 divided by a scaling, the large scale. Now, it is obvious for people who have some understanding of phenomenology that how can the energy vary if not by the gradients of large scales carrying out with certain velocities, and e to the 3/2 is the same thing as e multiplied by the velocity, because the e to the 1/2 is a velocity, and the velocity divided by the time, you get the scale, you get a time. That is the large scale turnover time. And of course, you're not surprised to find that, be it for Burgers or for Euler and so on in 3D, that time should control the dissipation. If there is a finite time dissipation, that of course is still a big unknown. But so Kolmogorov had this equation 22. By the way, it is very strange that in Kolmogorov's paper it has number 22, and our own paper, when we redivide it, we with things which completely differ from Kolmogorov, it also had equation number 22. So that's a very important result. Now let me show you finally how one can use Kolmogorov's equation for 22 together with the Proudman and Reed principle to obtain a phenomenology that will predict non-power law decay. That's very simple. What did Proudman and Reed prove or try to prove is that in 3 dimensions, because we're now again in 3-dimension Euler, the beating effect of 2 eddies having their scale near the maximum of the spectrum. So that means that in Fourier space, things, the wave numbers are nearly opposite and they can add up to something much smaller. So a very large scale. Then they proved using the quasi-normal approximation, the only one that was known in 1954, that the transfer, the thing you add to the energy, goes like k to the 4th power. This is how they destroyed the Lagrangian invariant. But what they did not know is that Proudman and Reed, they couldn't do any better than the quasi-normal approximation, which has all kinds of defects. But for this particular problem, you take the most modern point of view with renormalization mood and whatever, you get the same thing, the same scaling, or k to the 4th. It is very robust. So this is really how things change at large, at small wave numbers or large scales. So what one can derive from that, and it is discussed in my 1995 book, is something called the principle of permanence of large eddies. And that basically, in physical terms, tells you that if the large scale behavior expressed in Fourier space, so small scale wave number, falls off so slowly with the wave number that what you add, this Proudman-Reed term K4, is negligible, then the small space thing doesn't change. It is permanence of large eddies. And now when you use this thing, you can do something miraculous. Consider the equation of Kolmogorov, the equation 22. You have one equation and 2 unknowns, an E of t and an L of t. What can you do with that? Perhaps use the Lagrangian invariant, but that's wrong. But use Proudman and Reed and the permanence of large eddies, then you have another much better thing. It's shown here because in Fourier space, at the spectrum at the various times, short times, longer times, and longer times, they fall on the same line. That's permanence of large eddies. And you can calculate the energy by integrating from wave number 0 to the peaks here. After that, things decay very fast. It may just be a constant, one doesn't know exactly one, but the main thing comes from the low wave number thing. So you can express the energy at time t in terms of the wave number of the peak, k of t. And you do that in the Kolmogorov equation 22, and you obtain a very simple differential equation, which you can solve. It is nonlinear, but there is no problem. And you can find exactly how things decay depending on what you are assuming initially. If they have a power law initially, then you get a power law for the energy. But if the initial data is undulating, then you will get also undulations in the decay. And you can do it by hand, essentially. Of course, this is phenomenology, contrary to what I presented before, which is essentially rigorous theory. But, and I just remind you, so what we have proven, non-Kolmogorov and non-Karman decay is present for burgers. It is also present numerically in the 3-dimensional full simulation done by Matsumoto. And it can be derived phenomenologically, as I just explained. Okay, that's it.
I guess just one comment was that the flexibility of the weak solutions is, of course, a little bit too severe, I would argue, because at least you're always seeing decay of energy, whereas the weak solutions would allow energy also to increase. So,
let me answer that, precisely because I wanted to make this comment, but I didn't have time. When I discussed with various people, I don't want to give names, who pointed out that weak solutions, of course, can be both increasing or decreasing in their energy. I said the fact that there are non-physical solutions there doesn't mean that all solution will be, and what we managed to do is that there are physical solutions which of course do not have an increase in the energy, a decrease, but it is not a power law.
mm-hmm. Okay, I agree with that answer. Then I have a question. I mean, the Kolmogorov equation that you cited from his 1941 paper, of course, doesn't follow by dimensional analysis alone, because if you non-dimensionalize the dissipation rate by U and L, you still have time. And so the prefactor, the constant, could be a function of a dimensionless combination of UT divided by L. And there have been a number of claims by Christos Vasilikos and Tavolaris in the last 5 or so years that, in fact, in grid turbulence, this constant is time dependent. So I wondered if you had any comment about that.
Yeah, I mean, it is hard to. What I would like to say, which is vaguely conscious on this question, is that something which is actually stated in my book, that Kolmogorov's equation 22 does not need to be derived as he does from the 1941 A paper, the self-similar thing. He actually pointed out in the 1941 B paper that there are other types of derivation. Discuss them, but for me it's quite clear that a few months later, Kolmogorov produced a law for the third order structure function, which is not derived from the global self-similarity. And it is that kind of thing that he had in mind.
Although I think that
what's important is it applies both to self-similar turbulence and intermittent turbulence.
Yes. I mean, of course, the 4/5 law, which he derived, would not preclude time dependence of the prefactor in the decay law.
Yeah, sure.
So I guess Vasilikos and also Tavolaris and others have been making a big noise about this fact and claiming that it violates, sort of conventional understanding of the scaling. I guess my interpretation, they claim that it means that the decay is Reynolds number dependent in some sense. But I think in any case, it seems to be related to your conclusions.
Yeah, but I mean, for me, what is really the serious issue for Euler now, and not for the Burgers, for 3D Euler, is there a finite time singularity or not? And there are at least three possibilities. Systematic finite time singularity, none of it, or it could be also algorithmically undecidable. I mean, these are things about which we're thinking a lot, particularly with Alexei, who's somewhere here hiding. Tough questions. Tough.
Other questions to Uriel on the talk or on anything, I think? Anyone wants to say something? Rahul, anybody?
Well, thank you. I mean, the only thing I want to say, of course, is that if there are no more questions, I would like to thank both speakers for wonderful talks, and especially for our chair today, who not only chaired the talks, but also this wonderful session. Thank you very much all. And again, happy birthday, Uriel. And if there are no more questions, we can all, reconvene again tomorrow.